This lecture is being brought to you in part by the generous gifts of these sponsors.
So I guess I'll start by really acknowledging or thanking really the Smart family for making this possible. And it is indeed a rare occasion to come back to Pensacola. I haven't been here in 20 years, and I've graduated 40 years ago. Time flies, huh? Time flies, indeed. So what Karen hasn't really told you is that after New Orleans, I actually lived in Spain and worked in Spain, and then I lived in the UK, and now I'm in Belgium. So, yeah, I actually have 3 passports. So okay, all right. So I'm truly a world, citizen of the world. So thank you again for you to be here this evening, and also I guess I'm going to ask you, how much chemistry do you know, right? Some, I guess. Okay, so I see. Okay, so I'll try and be gentle, and tell you not necessarily about the chemistry, but about the process of inventing, maybe. Okay, so that'll be more palatable to more people, and how you put ideas together, and maybe how that's something I've always been fascinated with, how people do come up with ideas. How do you put 2 things together and you have a eureka moment? So I'll tell you about one of my eureka moments and see how crazy it is, and see how maybe logical it is, and see, at least in my head, it was logical. Okay, so I'm going to tell you a little bit about gold. So not mining for gold, but mining with gold. So I'm going to do something sacrilegious. I'm going to take a gold bar and dissolve it in aqua regia. So I'm going to destroy it, convert it into something else that allows me to do something that only gold can do. So you may or may not be aware, but gold chemistry is fairly recent. It's less than, I'd say, 25 years old in terms of its use to make other things. Okay, so very much in that respect, I'm a tool maker. So people always ask me, what do you do? So I don't tell them I'm an organic chemist, because that's what I am. But that's not what I am. I make tools that are used by organic chemists. So Dr. Gerst and Dr. Tanner taught me a lot of things. So I still find it hard to call him Jerry. He's always Dr. Tanner and Dr. Gerst. They're always that to me, and they'll probably always will be that to me. And I'd like to thank Dr. Gerst or Jerry, for teaching me what he taught me, because I really appreciated that and really realized what he taught me after I left, of course. And that's oftentimes what teachers don't get, is like the feedback of really their impact on people's careers, right? So I really thank Jerry for that. So he's made me the organic chemist that I am not today. Okay, so I guess I'm in a family business, because my grandfather, who was Irish immigrant, came to Canada and worked as a blacksmith. So very much I am a tool maker as well, just a little bit different. I'm going to tell you a little bit about my story with gold, because it's very specific and it's catchy, right? Who would destroy gold and make stuff with it? Stuff that revolves around the formation of carbon-carbon bonds. Okay, a little bit of chemistry there, and the context and the concept of sustainability, which is all in vogue now in chemistry. They talk about green chemistry. They talk about sustainability, which are not concepts that are, I guess, young or new, but they're very old concepts, and they're concepts that engineers completely relate to. It's a way to be more efficient. It's a way, in all cases, to be more efficient with everything that you touch and everything that you put in a reaction flask. Okay, so that's I guess the starting point. And of course, there's these 2 expressions: green chemistry and sustainability. It just means making sure that you don't damage the environment, making sure that the things that you use come from renewable resources as much as possible. But what we do nowadays, more and more in chemistry, is use the lessons of chemical engineers that have worked and fine-tuned and tweaked the petrochemical industry for so many years in making that process so efficient. Okay, so those lessons are not lost and should not be lost. Although we badmouth the petrochemical world a lot, and we need to move away from petrochemical feedstocks, the lesson learned from the engineering and the attitude towards optimizing processes is even relevant to this institution. And I'll let you see a little bit of what we do here in that context. Okay, so two famous names in the area of green chemistry are Paul Anastas and John Werner. They've kind of repackaged things. Okay, so they've not invented things, but they've put things into a different context. So that's where green chemistry, I'll let you read it. Green chemistry is that, but it's essentially doing things in a more environmentally responsible way with things that should be renewable as much as possible, and you try and not generate waste. So the efficiency aspect of all that. So we're trying to, and again, this is I guess a completely funny word in my mind. What is hazardous? Right? So water, if there's enough of it, it can be hazardous to your health as well. Right? So you need to be careful with the wording, and you need to be precise. And a hazardous substance is damaging us and damaging the environment. All right, so this is a famous thing. We teach this nowadays where I am and in places where I've taught before, very early on. So we're trying to teach a new generation of chemists and of scientists to be societally and environmentally responsible very early on. So we teach this in first year chemistry, general chemistry now. And this is something that comes from the, in quotation mark, green chemistry world, and what the concepts associated with green chemistry are. I'll let you read them. There's 12 of them. And most of them revolve around, making things simpler, more efficient, energetically more responsible, societally, environmentally more responsible. One of the big ones in my mind is number 9. So that's catalysis. That's central to the research I do. I'll explain to you in a second what catalysis is. But if you look closely at the other 11 principles of green chemistry, in my mind, I can relate 8 more to catalysis. Okay, catalysis can achieve 9 of these 12 principles. So it's really central to green chemistry and making things more responsible and easier and faster and more or less energetically costly. Okay, so Dr. Birdwhistle, when he was here, when I was here, taught me about thermodynamics and energy diagrams, and he taught me about kinetics. And this may seem complicated, but it's essentially it's a road map. It's nothing more than that. Okay, so you have an energy profile, so you have low energy to high energy, and this is a course of a reaction. So where you start and where you end. Okay, you start with a certain reagents and you end up with a product. So this is what that is. So your reagents are here, have this energy. Your product is here and it has this energy. And the difference here is a thermodynamic value. It's an enthalpy or a free energy so it's an energy term. Okay. In terms of kinetics, you have to worry about, or you have to be concerned with the barrier that goes from the starting point to the end. Okay, so that energy barrier needs to be crossed. So that means energy needs to be input for those reagents to end up there. Okay, so what I'm proposing, or what catalysis is proposing, is a shortcut, a lower energy shortcut. Instead of having a very high barrier or a very high mountain to cross, it allows you to go through shortcuts that have lower energies. Okay, and that is a kinetic process. That affects the speed of the process. This takes high energy, usually slow, requires high temperatures usually, and these barriers are lower, more easily crossed, and require less energy. A catalyst does that. Okay, what facilitates the shorter energy path is a catalyst, and that's what I make. Okay, those tools. Okay, so in a nutshell, that's my goal, that's what I do, that's what I aim to do every day I go in the lab. All right, how important is catalysis? If you look at the global GDP, it's about 45% of global GDP. In a way, shape, or form is linked directly to catalysis. That's a huge amount, right? So that's important. The scientific discoveries linked to catalysis are quite numerous. As of late, more and more Nobel Prizes are awarded to topics that are related to catalysis, and that will just increase in the next 20 years. Okay, so fearless prediction, for sure. Because things are being done in new ways, in simpler ways, in faster ways, in greener ways. Okay, so here is my friend Ben List, who won the Nobel in 2021, and he says this about creating magic with a catalyst. Okay, but you need the tools to do the magic. And I'll just remind you that the metal is in gold, okay? But I'm going to do something really bad with that metal in just a second. Okay, so, and it's quite heavy, so I'm told. All right, so my eureka moment comes in 1998. So already more than 25 years ago, or one of my eureka moments. I've had just a few, but this is a notable one. It surrounds a molecule. It looks kind of funny, right? It has as a central metal, so Ru is for ruthenium. And it's decorated with what I like to call organic spinach. So I am organic somewhat. Again, it's coming back, right? It's going to come back again, but I'm not an organic chemist. I'm in denial. So one key inventor, and actually sharing the Nobel Prize, here we go, Chauvin, Grubbs, and Schrock were awarded the Nobel Prize in 2005 for some chemistry that has really revolutionized the assembly of molecules. It's led to polymers, new polymers. It's led to drugs, new medicines, and a related molecule, a related tool that I've invented has led to, as Karen said, the use of that tool in pharma to make drugs. Okay, so that's about Bob and Dick and Monsieur Chauvin. So Grubbs, who was then at Caltech, invented this molecule and created a tool to make not carbon-carbon single bonds, but carbon-carbon double bonds. Okay, so in practicality, what that has done, it has simplified long synthetic routes from tens of steps to 3 or 4 steps, 5 steps. Okay, so it's cut down synthetic routes, so the length is really just shorter, the time to get to the final molecule is shorter, and the molecule complexity in which you can assemble these molecules has been greatly increased over time. Okay, so compounds like Taxol, which is a molecule you might have heard, treatment of cancer, can be assembled using this ring closing metathesis or this catalyst. It can form very simply carbon-carbon double bonds. Okay, and it's called the Grubbs catalyst. Okay, my students always put the apostrophe, they call it Grubbs catalyst, and they put the apostrophe between the B and the S, but Bob Grubbs is Bob Grubbs, right? So in English, the apostrophe goes after. It's one of my pet peeves there. But ruthenium sits at the end, so the right-hand side of the periodic table, and if you know anything about the periodic table, you know that the metals that sit in that area are tolerant of oxygen, they're tolerant of water, whereas the early members of the periodic table are actually quite sensitive to water and quite sensitive to oxygen. So that's one of the big advantages of the use of the Grubbs catalyst, is that you can do chemistry without taking great care to remove water or oxygen. Okay. All right. And I put here that it's a phosphine-based system. What does that mean? It has these phosphorus atoms, so P is for phosphorus, that are bound directly to ruthenium. So part of the activity of the organic spinach is to actually fine-tune the activity at the metal. So the action happens at the metal, but the decoration affects the reactivity of the metal. Okay, so this ligand, which is phosphorus base, has a bond to ruthenium and modulates the activity of the metal. Okay. All right, so my eureka moment is this one. Okay, so what we did is we did very physical chemistry at the beginning of my academic career, and what I did is I measured the heat produced during a chemical reaction. Simple, right? Gets hot, gets cold, I measured that, and I put a number on it. Okay, so the heat generated tells me the difference in energy between where I start and where I end. Okay, and if heat is generated, that means that the bonds that are formed are stronger. Okay, so here what I have is Grubbs catalyst, or the Grubbs catalyst, plus an organic molecule that's called an N-heterocyclic carbene, so for short, NHC. Okay, and there's an entire interesting story associated with that I'll tell you in just a second. So in 1998, these entities had been described in the literature as phosphine mimics. All right, so that's the link to Grubbs catalyst, and that's where the connection is made. Okay, so if you can make a ruthenium phosphorus bond, can you make a ruthenium carbon bond? So what's not written here is C for carbon. Okay. And in fact, I measured this reaction, the heat generated in this reaction. It's favored by 5. We were kind of lucky. So serendipity, I can't overstate the importance of serendipity in research and discovery. We were quite lucky here. Because of the geometry and of the decoration here, it only leads to one product, and where one of these entities is bound now to the ruthenium and one of these phosphine is eliminated. Okay, so what you do is substitution. Simple. Substitute one thing for another. As it turns out, this compound, isolated and fairly high yield, is very stable. Okay, that's great. We generate the compound, we get an X-ray structure, we know atom connectivity there. And what we realize is that this compound can be heated. So one of the Achilles heels of the Grubbs catalyst is that you cannot treat it thermally. So what does that mean? That means the reactions that are mediated by this compound can be done at room temperature or up to temperatures to about 30 Celsius. That's it. If you cook higher than that, you're fighting a losing battle of killing the catalyst versus moving the reaction that you want forward. Okay, so catalyst stability here is a real problem, and you can't cook. With these compounds, you can go to temperatures above 120 for multiple days, and nothing happens. The catalyst is completely stable, and it has to do with this change in the organic decoration around the metal. You go from a phosphorus to one of these NHCs, and the catalyst stability is greatly increased, and then you can do reactions that you could not do because of the poor stability of Grubbs catalyst. Okay, so that means you can do carbon-carbon bond formation where you have highly substituted double bonds. Okay, so the ring closing reaction, which is a typical reaction you can do in olefin metathesis, essentially brings 2 double bonds and forms 1. And that's a way to make rings, that's a way to make chains. Okay, so that's the carbenes. I'll come back to the carbenes in just a second. So let me show you these nice shiny bars. And of course, I tell you about sustainability, but of course it's not quite sustainable if you go all the way back and realize how gold is mined and how gold is treated chemically. It's a nightmare. It's an environmental nightmare, right? They use cyanide to extract gold, and you need to get rid of cyanide, and you need to so it's all a big mess. Okay? But you end up with shiny metals, but the environmental impact of that is quite high. Right, so you have some around your neck or on your fingers. So historically viewed as that, but what I'm going to do is destroy that. So to be more sustainable, I'm going to try and do chemistry with it that no other metal can do, and I'm going to try to do it as efficiently as possible. Okay, so nice shiny bars, and what I'm going to convert it to is this orange powder. Okay, so maybe not as attractive. But that's your bias, not mine. Okay, I like the bars, but I like this too. So this is auric acid, and there's a 4 there and another 3. So auric acid. So this is a kilo of auric acid, and that's worth about 20,000 euros at the time I bought it, or at the time someone gave it to me. I don't remember. because you have friends and you know. All right, so auric acid. All right, so let me tell you a little bit about what you can do with this architecture. I'm going to come back to gold in a second. What we've done over the years is taken a look, I guess since 1998, at the chemistry revolving around the use of this central tool. Okay, the general formula of the central tool. So a metal and one of these NHC or N-heterocyclic carbines, these phosphine mimics. Okay, in the early days, a lot of the bills were paid by collaborations with pharma, because the pharmaceutical business makes use of palladium chemistry to make carbon-carbon, carbon-nitrogen bonds. So this is a really, really important bond-forming, or both these reactions are important bond-forming reactions in the fabrication of medicines, of drugs. Okay, so you make them from scratch, and you have to form carbon-carbon, carbon-nitrogen bonds, and those tools are palladium-based. Okay, and usually palladium phosphine-based. So now we've moved away from that, and the stability that was encountered when I modified the Grubbs catalyst, I also see when you modify the palladium phosphine systems. If you have a palladium carbene system or NHC system, the compounds are, the tools are much, much, much more stable. Okay, so much so that the compounds can be made in air. Okay, which is not the case for the phosphine compounds. All right, so let me tell you a little bit about the chemistry. So the alpha metathesis I've already told you, but essentially today I'll focus on gold. Okay, but essentially the motif here is one of these things and bound to the metal. All right, so I really like this. It's a simple sentence. It talks about simplicity, but that's actually quite difficult to do. Right? To do simple needs a lot of thinking, needs a lot of thought, and to get to simple, you need to actually do a lot of pondering and wondering. Okay, so Da Vinci is, I guess, is the one who's attributed the statement, simplicity is the new sophistication, because it's quite difficult to get simple. And what we're shooting for is simple. I like the statement probably better because it comes from a chemist, a Nobel laureate as well, but it also tells you and put things into context in the way of sustainability, green chemistry. So Sir John Cornforth shared the Nobel in '75 with a gentleman called Prelog. And a journalist for chemistry in Britain asked him the pointed question of what was his ideal reaction. So Sir John said, well, my ideal reaction should be carried out in a disused bathtub by a one-armed man who cannot read. Product collected continuously through the drain hole in 100% yield and purity. Okay, so as synthetic chemist, which is what I am, not an organic chemist, that's what I'm shooting for. I'm shooting high efficiency, right? I'm shooting for things that are going to be completely selective, easy to do. Anyone can do it, anywhere in the world, any day, any time of the day, any day of the week, right? So that's the ideal reaction. That's what we're shooting for. Doesn't always work that way. It rarely works that way, but you know that's the goal. So let me tell you about a bit of a problem and a bit of a solution that we came up with in the synthesis. So lots of molecules here, and I apologize, there'll be more in the future. But really, this, I guess it's an interesting part of the story because it shows you what kind of problems we can have, even amongst ourselves. So the free carbene of this type of architecture was synthesized in 1991. Okay, so I keep telling you that my eureka moment was in 1998. There's a gap there. There's a gap of 7 years. Right? So as a number of important discoveries in catalysis had been done prior to 1991, this one was made at DuPont Central Research in Delaware. Okay, so when I was looking for a job, I had some of my former lab mates actually who worked there, and they kept telling me that this was the best academic job in the world. Of course, you work for DuPont, but it's not an academic job. I said, yeah, but you never have to write a research proposal. You never have to worry about money. And you can do, some business-related stuff, but the goal is a product in 20 years. And there's side projects you can do. So this is a side project. Other side projects that have come out of DuPont Central Research are one discovery made by the co-winner of the Nobel by Grubbs, whose name is Schrock. So he made this discovery and was rapidly hired away at MIT. Crown ethers, so molecules with oxygens that bind metal and are used in chelation therapy, were discovered at DuPont Central Research. So there's all sorts of discoveries that were made there. And a number of, so that's my KLM flight. Yeah, so let's see if I can get that out of the way. There you go. All right. I don't need the reminder. I'll be there. So this is an important discovery, and DuPont, in their wisdom, patented the process to get to that molecule. Okay, the sales pitch of the patent was we can make paint stabilizers. They've never used it as paint stabilizers, but that was the pitch. Okay, so I guess they had to convince management that there was a business-related issue to this discovery, and that was the sales pitch. In the 1991 report in the open literature, Arduengo takes a molecule like that, which is a salt, and he acts upon that a very strong base to take away this hydrogen, and you get to here. It's a very simple reaction. It's a proton removal, hydrogen removal reaction. Makes a splash, but then is forgotten. And in 1998, we start scratching our heads like, yeah, we'd be really interested in looking at this molecule. And at the time I was in New Orleans, and at the time there was a big conference and people from DuPont were coming, and one of my old friends from the Chicago labs was coming to town, buying robots, believe it or not, to automate things at DuPont. And we had lunch, and there was a table full of crawfish, and I was quizzing him about these carbines. I found them quite curious. In the literature, they're described as phosphine mimics. I'd worked on phosphines for almost 10 years. I said, what? You know, I think I have some questions about that. Maybe you can answer. I said, nah, I don't really know much about that. You know, yeah, it's done by my colleague next door, but I don't really know much about them. Nobody really knows much about them. Okay, so I went back to the lab, and he told me, well, the procedure for that is in the patent. I said, yeah, I tried looking at in the open literature, finding it. It's not there. I said, yeah, it's in the patent. Okay, so I get the patent, reading it. It's like, yeah, okay. Read the claims. I don't tell me anything. Read the experimental section, and there's a paragraph. There's about 7 lines. That's the experimental protocol. That's the recipe to make that molecule. I look at it. Yeah, it's fairly simple. You throw all the components in one pot and you cook. All right, easy enough. I'm a bit worried because I look at the experimental yield. So what the yield of that is, it's a 105% yield. 105, yeah, so you figure there, something's amiss. All right, something's amiss. All right, so my student hammered at that reaction for about a couple of months, and we got some material. In the meantime, he made all sorts of tars. The product is said to be rutile white. Okay, so very white. To be used in paint, right? Okay, so it makes sense. But we got stuff that color. Yeah. So we purified stuff and whatever. So we got some clean material in the end. We did the reactions and whatever. But we had a big problem because, well, you know, that wasn't manageable, or surely not sustainable, and surely not green. Okay. So you throw all 3 components in the soup and you cook. The issue is, it's called a condensation reaction. So you throw the components together, and the product that's generated is water. Okay, so the issue is, this is a salt, and like table salt in water is quite soluble, guess what? This in water is exceedingly soluble. So to get the material as a solid out of the soup, you need to get rid of all the liquid in the soup. So on small scale, it's doable. On large scale, if you want to make grams of that, you need to get rid of all the water. And that takes time, and that takes heat, and that takes heat over a long time. So things go wrong, things go bad when you heat things for a long time, and you get that. Right. So I had a student at the time who was actually short order cook in New Orleans, but eventually was trained in a fairly high-end restaurant on Royal Street. So if I mentioned the name, you would probably recognize that. So I said, I tasked him. It's like, you optimize that reaction. Yeah, I want some material, and how do you find a solution? Okay. So I said, well, he said, well, let me go in the lab and I'll tackle that. So over the course of a couple of weeks, I was like, going in the lab and seeing these large amounts of material being put in a pot and stuff like that. I thought he'd do things on milligrams, right? So to work things out. Yeah. So I said, yeah, Roy, why are you doing this on 10 grams when you don't know whether it's going to work or not? Well, he said, I'm trying to make gumbo here, right? So I don't make gumbo for 2. You make gumbo for 2, 20, 40, 50, you go big scale, right? So he turned out to be a process. So you got a job in process chemistry. So he did things on kilo and tens of kilo and metric tons, right? So he was go big. So he did go big, and he didn't go home because he succeeded in doing that. And what he did is essentially broke down the reaction. So he went simple by doing more steps. So what he did is that instead of throwing everything in the soup and cooking, he took 2 of those components and made something that was easy to isolate, which is the first component over here. And then in the second step, he added the third component, and in a room temperature reaction, and the third and fourth component. And in the end, he made the thing, 2 reactions, room temperature, involving 2 simple filtrations. Right? All right, go Roy. Right? And because Roy could make large amounts of that, we could easily get to here by action of a base. Okay, so the same trick that Arduengo at DuPont used, we could use to get to here. Now I show you this specific example with the specific decoration, because if you throw all components in one pot and cook, you get nothing. You get this. Nothing else. The product is never formed. Okay, so this is a specific case. It's one specific example we invented and disclosed in 1999, which is a workhorse in the area. So whatever you want to try as a decoration or as a catalyst metal modifier, we always start with this one, because oftentimes that's always the best, as luck would have it. Okay, so we have a special recipe for that, and let me show you some pictures about this special recipe. So this is the reactor, so this is the pot, essentially, we had in New Orleans. So I had a 22-liter reactor, which is filled halfway, and which is an overhead stir, and you stir, and there you go. That's one of the first, that's the first step, okay? So in St. Andrews, so when I was in the UK, we got a fancier version, and for, I guess, the folks who were here yesterday at my presentation, that's a different overhead stir. So usually I don't show that one, but so I have a fetish overhead stir. So all the bells and whistle, temperature control and whatnot. Okay, so that works okay, and you get the same thing. But when we moved the lab from New Orleans to Spain, I didn't. So the 22-liter reactor was actually in a container in Valencia, trying to go through customs, and my students were getting kind of antsy, and so they said, "Well, we don't have the glassware," So I actually went in the lab and myself cut open the top of a bucket, and we actually did this reaction in a bucket. Okay, so this is truly bucket chemistry. Okay, all right, okay, bucket chemistry. And this is my fetish overhead stir. You'll see it again in a little bit. All right, so that's 3 kilos of the yellow intermediate, and that's 3 kilos of the final product. I guess I told people yesterday the street value of that was higher than a kilo of cocaine or something. It was really, really expensive. The commercial value of that was outlandish because the synthetic method, the way to get there, was so complicated. But now, just depends how big of a bucket you have, and you can make it. Okay, so it's really simple. And even an apprenti chef in New Orleans can make it on kilo scale. All right, so let me tell you a little bit about gold. Okay, so all these transformations involve the use of this tool. So it's quite varied. The nature of the reaction is not important, is that there are many different types of reactions that can be facilitated by gold. Okay, so of course, gold here is not gold metal, but it's a variation of that orange-yellow powder, and the gold compounds are very boring looking. They're white. Okay, so you lose the lackluster there. And the workhorse in the area has this structure. So the compounds are very simple. They're one gold, one of these magic ligands, and then another thing that's attached to it. So they're linear molecules. They can do these organic transformations, although I'm not an organic chemist. But they have important biomedical applications. So in the last 10 to 15 years, some of those compounds have shown great activity against quite a large number of cancers. Whether it's breast, ovarian, those compounds have actually shown great potential. And some are in clinical trials. And some of those compounds show luminescent behavior, and I'll come back to that in a second as well, in terms of the importance of sustainability and things like that. But this is an area that, like a lot of the areas that are being explored in chemistry, that are discovered, ignored for a long time, rediscovered, and all the hoopla is like, oh, it's new. And then you start reading about, the pioneers, 100 years in the past. So people are rediscovering things that people already knew. So this is the workhorse, where X here is chlorine or chloride. All right. So I won't talk to you too much about the chemistry. I'll just show you, I guess, the 2-ton approach to the synthesis of these compounds, which is just doing the thing that I did before, taking the imidazolium salt, so the salt precursor, acting upon it a strong base, generating this, so ripping away the proton. And then I'll do a ligand substitution, just like I did with the Grubbs catalyst. In this instance, this is DMS, or dimethyl sulfide. It's a good thing to leave, right? And you end up with the linear structure. There's another route that involves substitution of metals, so that's kind of wasteful because you need to make one compound and then you use that compound to make a second compound, and that generates waste during the first step. Okay? So in the literature, as we started looking at ways or better ways to make that, so a very smart person, a Nobel Prize winner, once told me, first you need to get the compound. So by whatever way, means, or whatever, you need to get your hand on it, make sure it's pure, and then you test its chemistry. Then you come back and make sure that you improve the synthesis of that compound. But first, you need to demonstrate that there is value there. Okay, so in this chemistry, we demonstrated that there was value, and then we went back and redesigned, re-examined the assembly of the tool. So in the open literature, so some people had noted that in fact, I've just told you that you get from here to there by action of a strong base. So that means there's all sorts of things that you need to do because the base is sensitive, the base will react with a bunch of stuff, and you don't want that. You want the reactivity to be selective. Something that's easier to handle are what are called weaker bases. So those are more innocuous, they're easier to handle, they're not so reactive with oxygen, air, carbon dioxide. You don't need to take special precautions. Okay, so there's a simplicity in using weaker bases. But I've just told you that the imidazolium salt, to rip off that, you need a strong base. So we were really puzzled to see in the literature that weak bases were used. So our thinking was, you do the delivery of the ligand by generating this, and then you bind. Okay, so our bias. Because in fact, in the literature, they showed that a weak base could do it. If you just take a weak base and try to do that, that doesn't work. But if you do it in the presence of a metal, that works. Okay, at the time, I didn't really know how that worked. What's the mechanism? What's the process? I had no idea. Okay, but we were curious, and that's why we went there. So there's all sorts of drawbacks to this, also large, long reaction times, and the solvents that they were doing this chemistry in was really atrocious. Right? So, all right, lots of numbers, lots of conversions. You'll see lots of 99s over here. One's highlighted, it's over here, I guess. I guess you have 3 that are highlighted, but this one's the important one. So the reaction involves a very specific base, which is a weak base. So in this case, it's potassium carbonate. Reaction temperature 60, reaction time 1 hour, yield 99% of what you want. Pretty cool, yeah? What's cooler is that this reaction is done in a beaker, in air. I could plop it there with an overhead stir or a stirring bar, and the reaction would go. No special precaution, no exclusion of air, no exclusion of moisture. It would work like that. Okay, so very simple. Okay, so I won't tell you how mean I was, because I was a mean person there. So the people who were here yesterday will forgive me, and the people who are here will forgive me for skipping over that. Okay, so it works, and it works really well, and it works really fast, and it's complete transformation. And you can get from here to there with a weak base. All right, so all sorts of decorations are possible, just to show you that you can decorate the thing in a number of ways, and the method works. It seems to be quite general. Things are slower or faster depending on how large you're the ligand, so the entity of the NHC, you're trying to dock to a metal. If things are very, very busy, you're still trying to get to that position, and that takes time. Okay, and it usually takes higher temperatures or longer time. But you can get around that by just waiting, by just doing the reaction at elevated temperatures, and you can get to the gold compound. Okay. All right, so again, some pictures about scale. You need to get to the material. So, okay, we can get to the material using the strong base route, but now using the weak base route. And in fact, we do this in what are called scintillation vials. So this could be, this could be a teacup. It would be the same, right? So, very simple vial. You see I guess the magnetic flea, I guess is what the Brits would call it. The stirring bar is what we would call it. You would, cook it for an hour with stirring, and then filter it and precipitate it, remove the volatiles, and there you have it, 97% of that. That works great. It's done in air, huh? It's done in air. 1 gram you can do, 20 grams you can do, 100 grams you can do, and you can do even larger. Okay, so my fetish overhead stir. Bigger container, just a flask. Huh? So lots of material in there. 1 hour reaction time, filtration, precipitation, just as I did in the small vial. So I collect the material which looks like granulated sugar. It's really beautiful material. Collected it in my favorite brownie pan. Because whenever we do large-scale synthesis, believe it or not, people will remind you that cooking is chemistry, and that is true. But we actually got all our large-scale synthesis supply at a restaurant supply store in New Orleans. All right, so I have spatulas, and I have cool stuff that has traveled with me over the years. But this we still have. I really like this pen, and so this is 222 grams of that material. You don't need to do anything more. It's used as is. It's completely pure. You're going to say it's boring. It's not yellow and shiny. It's boring and white. But that has great value to me because I can do organic transformation. Sorry. All right. So that's the story here. All right. So I'm trying to understand how that works, and that's also something that is, I guess, that's been bred into me. I need to find out why and how. And I'm a mean supervisor because those are the simple questions that I ask my students, and those are the toughest questions. Right? So you need to probe how things happen. So you need to do the experiments to convince me or yourself that things work a certain way. Because if we know how things work, we can improve them. Okay? All right, so I won't bore you with the mechanism, just to show you that, in fact, this salt, in the presence of the precursor, you do a swap here. The DMS leaves, and you have gold chloride as a counterion. So things change, the gold comes on board, but you don't have a metal-carbon bond. So you don't have binding directly at that position of gold, it sits outside. Okay? You can do this in a variety of solvents. In the end, you can do this in, I guess, if people know grinding in a ball mill, or if you don't know what a ball mill is, you can do this in a mortar and a pestle. So this is just mixing the two solids and just grinding them. right? You probably have one in your kitchen for herbs, right? You can do the chemistry there. So without any liquid, without any solvent whatsoever. Okay, so real easy to do. That's done, and it's quantitative. You get 100% of that. Okay, and if you subject this to a weak base, you get to the end game. So the weak base is important, the solvent is not. Okay, this is also a solid, and after you grind the first bit and you get that, you can add the potassium carbonate, grind some more, and guess what? You get that. So that's kind of interesting because in chemistry, one of the issues we have is solvent as waste. That's the largest component of our waste outputs, it's solvent. But in this chemistry, you can do the chemistry without any solvent. That's really cool. All right, so I won't bore you as to more experiments to try and disprove something. And we know now that how things happen is not through the formation of this. This is never formed. Because this, if it lives, you need to take great care of it. You can't show it air, you can't show it water. This is really, really reactive and unstable under those conditions. And what you need to do is make sure that those two reagents are excluded, so air and water, okay, because this decomposes. I've told you that the reactions with gold we do in air, right? We can even do in solvents that contain water, so that's not a big problem. So this is never formed, okay? So through the help of some friends who do computational chemistry, we've come up with a mechanism that makes sense, that has been validated, I guess, in a number of ways, but that tells us that actually the gold that sits outside eventually binds inside in the presence of a base where all components come at once, and that's where the exchange happens. And the free carbene, the free NHC, the one with the lone pair that's been deprotonated, is never formed. Okay, so that was kind of an eye-opener for us, because that meant that if this is the story with gold, maybe it can be the story with other metals. So we looking at the breadth of this weak base route. So I guess I've shown you this before, but I like it so much I'm showing it to you again, right? So you can do other decorations. So here you'll note maybe another nitrogen in the ring. And we have X-ray structures defining and determining the absolute composition and atom connectivity of those intermediate here and final product. So this works for a variety of structures and using very simple solvent and weak bases. Okay. It also works for copper. Okay, so if you remember the periodic table, gold sits at the bottom, and then you go up, that's silver, you go up, that's copper. It works for copper. It works for copper. It works for palladium. I've told you about my paying the bills with palladium early on. This is one of the architectures we discovered. So I should also tell you what the common practice is in catalysis with palladium is, which is done by organic chemists, which I don't really like. Not the organic chemist, but the method. I have lots of friends that are organic chemists. So how things are launched usually in catalysis is that you throw in the soup a metal precursor, so a metal containing something. And then you throw in some more decoration, something that will bind the metal. But you throw that in the soup, so it's not preformed. So oftentimes, if the additive is a phosphine-containing compound, phosphines are sensitive to oxygen. They decompose. So what is done is a lot of phosphines are added. So in fact, you have extra stuff in the soup, stuff that may in fact hinder your catalytic reaction. So what we've done is we've done exact stoichiometry, exact 1-to-1 ratio between the ligand and the metal. And what you add is one component instead of hoping that the catalyst will form while you add the two components. Okay? What does that allow you to do? It allows you to use less. Okay? So we use much less catalyst in our transformation, much less of the tool than the generation of things. Hopefully, cross your fingers, things will form and then go. Okay? All right, so it works for gold, it works for copper, it works for palladium, it works for platinum, it works for ruthenium, it works for osmium, it works for, which one? Manganese, iron, nickel. It's quite general. Okay, so, but this is from an understanding of how things work with gold. Okay, and we've been able to extend that. All right, so the bottom line here is that all these are great things. They're greatly improved energetically. The involvement is reduced, the commitment is reduced, high yielding, very much less solvent is used as well. Okay, all right. So here, some help from computational. So my friends always badmouthed computational people because, well, they always explain things after the fact usually, but this is actually a prediction from a computational friend and actually directed some of our research in very interesting and unexpected areas. So chapeau to him, right? So my hat's off to him. So we were looking at the interaction of this fragment with things in an organic transformation where we could put down on paper what could possibly be stable. Okay, so along the way. So all these numbers you'll see are large and in black. So that means that those compounds are unstable. Okay, so the computational work told us that this number is very large, yes, but also very negative. Okay, so in terms of energy, that tells us that that compound is super stable. Okay, so in gold chemistry, what you learn very early on is that gold in this form is like H plus. Okay, so H plus combining with OH minus to make H2O. Being stable should not be a surprise to anyone, right? But when we looked at that, it's like, oh yeah, it's H plus and H2O. It should be stable. So I tasked one of my postdocs when we moved to St. Andrews to actually put that compound in a bottle to see if, you know, our computational friend was full of H2O or not, or whatever. So actually, he did that quite nicely. He used a very expensive source of OH, but got there. And we got some really nice crystals. And in fact, the structure is that of water. It's a bent structure. It's the same, right? So that's kind of interesting and important. And it comes from pure curiosity. So we're making a potential tool, maybe, for which we have no use for. So this is a solution to a problem that has not yet been identified. Okay? I make tools. Sometimes I just make tools for making tools' sake, but eventually we try and find a use for them. So that's the, yeah. So you never really know if you have a solution until you know the problem. So in this chemistry, the solution or the importance of that compound came about here. So what I'll tell you is that in gold chemistry, so using gold as a tool, always you need not only a hammer, but you need a hammer and a wrench. Okay, so you need two tools. So in gold catalysis, this is a neutral compound. You need silver as an additive. And what silver does is it goes to the chloride, makes silver chloride, that precipitates, and you're left with that. And that's the tool. That is the one tool that does the magic. Okay? But of course you need silver. And what's interesting in the open literature, you see very highly visible groups, very famous groups that have done lots of gold chemistry that all of a sudden publish chemistry that is only done with silver. So you're thinking, oh yeah, they did the control experiments and they just used the wrench and saw whether the reaction worked that way. It doesn't. You know, they used the hammer and oh look, it works. You don't need the wrench. Okay, so this is a problem with silver, that silver is not innocent. It has some reactivity, and it can be the catalyst in of itself. So you don't need the gold. Okay, so you need to be careful, and that's always what I tell my students, do the control experiments early on to make sure that you don't run a bunch of reactions, and then in the end you realize only one of the components does the bit, right? Kind of wasteful, especially if it's gold. Right? All right, so what we've done here is use this hydroxide, this water analog, and used a source of H plus to essentially remove water, or permit water to be removed, and what you're left with is this. Well, this is that. But we've gotten here without using silver. Okay, so you don't need silver. This is dirt cheap. Huh? Okay, So this is really expensive, light sensitive, right? You all remember, some of you, the photographic material, right, on films and things like that. Light sensitive, of course. And you get to here. So you can do this chemistry with the same compound, but without using silver. So I'll tell you, you can do all these transformations using this with a little bit of H+, and that gets you to the same activity because it generates the same tool. Okay? So all these reactions are mediated by gold, but had been mediated by gold plus silver. Now you don't need the silver. All right. And then an accident. A really bad day in the life of a graduate student. A very stressful day. He had just become a father, and man was he stressed. But he got more stressed because of that. So he was doing a reaction where this magic tool that does gold chemistry is stabilized by a solvent molecule. So then you can isolate it and you can put it in a bottle rather than generating it right before using it. Okay, so catalyst on the shelf, then you throw in the reaction and then you go, you don't need silver. Well, the problem wasn't the use of silver, because initially we had done it this way. We have other ways to make it now. But what he was trying to do, he was trying to make 20 grams of that. Okay, now 20 grams, they may not seem like a lot, but it's 20 grams of gold, right? So that's a lot. And especially if the reaction doesn't work. What do you do with 20 grams of gold that doesn't work? You recycle it. It's not a good day. So the solvent molecule, the solvent that is used is called acetonitrile, and it binds to gold to stabilize it. And he'd used an old bottle of acetonitrile that contained water. Okay, so water is the culprit, as we later found out. And I say, well, what do you have? He said, well, it's not the product. It's not that. I say, yeah, but what is it? You say, I don't really understand. It doesn't have one gold, it has two. I say, okay, high yielding? He said, yeah, I get 97% of that. Yeah, but that's not what you want. He said, yeah, but that might be more interesting. Okay, so what is it they say? Luck favors the prepared mind. I guess luck favors the open-minded as well. Huh? So you really need to appreciate your failures, and this is what Ruben did here. He said, yeah, but we might have something interesting. I said, yeah, but okay, so how did you confirm that? He said, well, I got an X-ray structure. I know exactly what the compound looks like. It has two gold, and in between there's an OH. I said, yeah, okay. All right. So we thought a little bit about it and looked at the structure and thought, well, hang on a second. If you take a knife and slice in that direction, you have this with that, and you have this part of the molecule with this. I said, okay, well, maybe we can make it on purpose. And he was like, yeah, you want to make that on purpose, but we don't have a use for it. Yeah, but let's try and figure out how that happens. And in fact, if you get to here, right, my old friend I just showed you, the water molecule like gold compound, and if you react that with only 1/2 of an equivalent of HX, so only half of this will be converted, so this will remain this, or half of the amount will remain this, and the other half, you'll rip off the proton, generate water, and get to here, and then these two things combine and you get to here. So the way we were thinking about the molecule is the neutral, the OH compound here, combining with that could get you to here, and that might be the way. In fact, that works great. As advertised, as thought, you can get to here, 97% yield using this route. And here, the water amount is important, so that's a little bit more iffy. Okay, so you have more control here. Okay, so you can get to here. Again, we have a great solution to a problem we have not yet identified. All right. So here's the problem. Well, I told you how we were thinking about this, and that's how we came up with the way to make it. We thought, well, half this molecule is a neutral, and half of this molecule we know is kind of like the active tool in the catalytic transformations. And we know that for most transformations in gold, you react the cationic gold with carbon-carbon triple bonded molecules. So not 2 bonds, not 1 bond, but 3 bonds. Okay, and you can convert those molecules and derivatize them to make a series of very interesting organic molecules. Okay, so all sorts of reactivities have been shown before with alkynes, carbon-carbon triple bond, and water to make ketones, various derivatives of that using alkynes as the starting material. But tertiary alcohol or phenols have never been looked at. Okay, so what does that mean? That means that in a reaction that was reported in 2010, Sau reported this magic potion of gold, this, which is that, some bases, solvents whose boiling point is, I guess THF is the highest, it's 60 degrees, but the reaction is carried out at 100. Okay, so this is done essentially in what is called a sealed tube. So it's done in a bomb, right? So pressure builds up in the reaction, and the reaction times are exceedingly long, and the yields are all over the place. Okay, but an interesting transformation, you add the OH bond of what is called a phenol across a carbon-carbon triple bond, and that's what that is. So hydrogen comes from here, O comes from there, and you do an addition. So these compounds are important, and they're interesting in terms of making molecules, in terms of developing methods to assemble molecules. Okay, so you form a carbon-hydrogen and a carbon-oxygen bond. All right, so my students were thinking, well, hang on a second. We have two fragments in the molecule. One is neutral and one is cationic, likes these molecules. So maybe you can have a dual activation. You can bind gold in this sense, like a classical way to bind alkynes, and then a neutral way, you can make that compound. So you can actually react both components with both components of the tool. And in fact, you launch that reaction and you get 15% of the desired product. Right, I've been telling you about efficiency. You're going to say, Nolan, 15% ain't much. And I will agree with you. Right, but the person who carried the work was Yoshi, and Yoshi was a Japanese visiting scholar, and he was all excited. Man, was he excited. He said, Steve, I got 15%. So Yoshi had an accent. I said, Yoshi, it's not 50. No, it's 15. Okay, and you're excited. Oh, yeah, I'm really excited. Okay, all right, what are you going to do? He said, give me a day. I'll do some optimization. I'll come back. All right. So Yoshi does what Yoshi does. He goes in the lab, does the optimization. He comes back to me. He says, yeah, Steve, look, I have this table. So I've transformed the 15 into 97. How does that sound? He said, yeah, Yoshi, go Yoshi. I said, Yoshi, how did you do that? He said, well, the first thing you do is a solvent screening. I say, is that what you do? He said, yeah, it's the obvious thing. You do a solvent screening. Okay, it wasn't obvious to me. It was obvious to Yoshi. So Yoshi, in one day, made this a brilliant success story where solvent plays a key role. So I've shown you the hyperligand, so the magic ligand. That's the magic ligand in this chemistry as well. And 97% yield. So I compare it to the Sau system, but that's my ignorance showing. I don't know how the Sau system works, right? So the initial reaction with the magic potion, I don't know how that works. So lots of successes, and you'll see the numbers in terms of isolated yields are usually very, very high. The reaction times are usually fairly short as well. And toluene is the key. Okay. All right, just to, again, badmouth the Sau system or just plead my ignorance again. This compound we get after an hour, and Sau gets it after 144 hours, only in 35% yield. So night and day, right? That's just, I don't understand how the other system works. But here again, I emphasize the fact that we know what we put in the soup. We know the tool. And if you do things kind of this plus that, and hope for the best, then how do you tackle a problem like that to try and understand what is happening? It's very difficult, right? So, all right, so reaction times and all that. So there's some trends that are observed that are completely opposite to what Sau had observed. Again, I'm a very mean person. Okay, so I asked my student, great, you know how that works now. Both parts of the tools work in two different ways. They attack two different molecules and they activate things, and you mix them together and voila, right? I said, well, what happens to the gold? Because I'm always interested in what happens to the gold, right? Follow the gold. Well, he says, I don't know what happens to the gold, but I've worked out the reaction and got rid of everything, the product, whatever. I have some residue, I'll analyze it. So he goes in the lab, analyzes it, takes an NMR, and he comes back and he says, Steve, what I have at the end is what I started at the beginning with. So you say, that tool is there. Yeah, he said, the catalyst is still there, it's the same. So I said, there's no purple. So purple in gold chemistry is death, right? It's the formation of nanoparticles. That means the catalyst has died. I said, there's no metallic gold, which is also a byproduct. Sometimes you get chunks of gold, believe it or not, gold depositing. Right, so gold, right? But that's a bad day in catalysis because that means it's not the tool, right? The tool's still there. So I say, well, add some more stuff, right? Let's see if it turns again, right? If it converts the two starting material to products. So, so Adrian did that in the overnight reaction while he sequentially added substrate, and it turns. So this is the version, or my version, or our version of the Energizer bunny reaction, right? So this is the reaction that keeps going and going and going until you reach mass transport problem. So that means there's so little catalyst that the substrate can't reach the catalyst, and then the reaction becomes very, very slow. I say, okay, strip off everything, and what's the catalyst? Oh, it's it. Strip off everything. What's the catalyst? Digold hydroxide. Same starting tool. The thing doesn't die. Really, really stable. Okay, so this accident, this bad day in Ruben's life, sleep-deprived new father, actually turned out quite to be a gold mine for us, no pun intended, because it allowed us to explore quite a breadth of chemistry. Because here you have phenols, but you can sort of look at all kinds of derivatives of that and molecules that are related to that. So here, just again, a way to badmouth Sau. Turnover number, so the number of cycles that this compound can do is over 3,000, and the maximum number that Sau observed is 7. Okay, so a complete different ballgame. A complete different ballgame in terms of the stability of the catalyst of the tool. All right, so we can do other things that are related to phenol in terms of acidity, the same kinds of acids, and you can do addition across triple bond of different types of organic molecules. And those complexes are also super important, super versatile, super useful. And here we actually have simplified the process because however the importance of solvent was in the initial discovery, here we go without solvent. So here we have the substrates, the two reagents that are liquids. We mix them together with the catalyst, it turns, and you have product. So no solvent whatsoever. Okay, so I guess that's why my student wrote that in green, because it's greener, right? It's much, much greener. And it's quite versatile. You can have all sorts of things. I'll not tell you too much about that because it's a way, so I guess it's a way that we've kind of tried to explore in trying to activate or use a tool that did not require OH or did not require chloride or functionalization or doing other things on this end of the molecule. So this was one of our earlier attempts. You can make a carbon bond and then these compounds can possibly be used as compounds that are going to become catalyst. Okay, so this is stable, you can put it in a bottle, it lives forever, and there's ways to do that. And I'll just show you here that, yeah, you can have very high yields of these reactions. Maybe I'll tell you about this one. That might be interesting. So this is the delivery of, so the phenyl here is AR, and you substitute it for chloride, and it's done in ethanol, okay, in the presence of the weak base. It tolerates water. So in Ghent, actually, I guess the Belgian people in Flanders really like their gin. So there's quite a number of distilleries, gin distilleries in Flanders. So this reaction was done 40% ethanol, and 40% ethanol is, yeah, it's gin. It was done in gin. Okay, so this reaction was actually done in gin. Non-degas, oxygen containing, completely compatible. Okay, so this reaction works in gin. I guess some people say it's a waste of gin, but anyway. Compatibility with water. And we move away from ethanol, ethyl acetate, and water. Why? Because we can do simple. We can do structures that had never been done before. So my students really love that because they explore areas where they are the first to make a tool. Okay, so usually it becomes associated with their names. Okay, so this is one of the Tsuras catalysts. But showing you simplicity as well. So had I not been a professor, I probably would have been a process chemist because I like simplicity and I like moving things and lots of things around. So this is the reaction at the beginning. And then it's done in a mixture of water and ethyl acetate. And after the reaction is over, you get this. And how do you separate the product from the rest of the stuff? You put it in a sep funnel. You separate the bottom stuff. You get rid of that. Keep the top layer. And that's where the product is. And that's the only thing that's there. Okay, and you can scale that up. Okay, so it's very easy. And it's done in air in just a round bottom flask. All right, so there's also all sorts of other architectures. Again, trying to get to simpler, but really failing because you do an extra reaction and that's not so. Okay, so these are all new compounds as well, never been reported, using weak bases and done in air, in ethanol in this case, and a mixture of ethanol and water. All right. So this a very busy slide because the person who made that is Nikos. So Nikos was a graduate student of mine who recently graduated, and he was just a superb student. Really, probably the best, surely the best student I've ever had. Nikos had the green fingers and green hands. He could make anything. And what he did is he made compounds. So here there's a variety of metals that are shown, copper, and there's gold, and there's silver, and whatever. But he made these architectures, and that's the take-home message. So these simple molecules with L being the carbenes, the NHCs, and the other end of the molecule being carbazole. Okay, so carbazole has some interesting luminescent properties. And if you attach it to gold, the gold compound has really super interesting luminescent properties. Okay, so lots of synthetic work, lots of structural work, also showing you that these compounds can be made just by grinding. Okay, so no solvents here again. It can be done in flow. Okay, so flow is also a big area now in modern synthesis. So the synthetic chemists have learned from the petrochemical industry, and now flow chemistry is done in pharma, right? So they've just adapted the flow chemistry of refining crude into making drugs. So they can move lots of material in a very short amount of time, and you don't need the very, very large reactors. So there's an economy of space, an economy of time associated with that, and lots of pharma is moving that way. And even in making tools, you can do flow. Okay, so here we're passing solutions in an oven at a given temperature for a given amount of time, and the output is the product. Okay, so going greener, going faster, and you can move lots of materials. So I'll just let you read that. The compounds also have anti-cancer activities. All right. So we started looking at that. So one of my students actually put that in an NMR tube, so for analysis, and was looking at it. It has a weird tinge under neon light. So he put it under UV light, and things like glowed like yellow. It's like fantastic glow. So we sent it to our colleagues in Germany who did a full photophysical analysis of the luminescence. So they looked at what was the lifetime, the properties of how this behaved with light. Okay, so what came out of that is that the compounds could possibly be used as tools to use light as energy. Okay, so we've never done photocatalysis, right? So catalysis with light. And we said, well, what the heck? That's what the chemistry is telling us. That's what the physical chemistry is telling us. These could be used for that. So why not use them? And in fact, we do that. So I should also tell you that the area is super active. It's like there's such great activity in photocatalysis nowadays. And I'll make a fearless prediction. So there's a recent Nobel Prize winner that will probably win a second one for that chemistry. That's my fearless prediction in some not so distant future. But most of that makes use of what is called, not a catalyst, not a photocatalyst, but the area, they describe it as a sensitizer. It's the same thing. They use a tool, right? So that's the tool. The tool is one based on iridium. Now, the price of iridium is between 4 and 5 times that of gold. It's super expensive. 1 milligram of that costs €1. 1 milligram costs €1. Yeah, it's super expensive, right? So people invest and they buy, you can buy from the commercial suppliers 100 milligrams and it's €100. And you can do just a few reactions with that. So, yeah, price is important. Gold for, 3 to 4 or 5 times cheaper. And I've shown you how easy it is to make. You can do it on scale and just grinding, whatever, and it's easy. So we launched, just as a proof of concept, this gold compound as a sensitizer, as a catalyst, as a tool to do these transformations. So this is mediated by light, right? So there's no other source of energy here but light, right? So photocatalysis or photochemistry is very old, right? So again, a rediscover, a rebirth of that, right? It comes in cycle. It's like fashion. It's like 20 years, right? So just about the same thing. And you can make these very complex architectures, cyclic architectures, very effectively, okay? And what we've seen is that, in fact, you use gold, works like a charm, okay? Instead of this expensive, well, more expensive iridium compound. All right, you can do all sorts of other transformations, and we've also shown that the specific properties of that gold are such that it can do transformations that iridium cannot. That's really cool. Okay, so here again, it was let's go see what this thing can do type of a trip, type of an exploration and study at the beginning, and we discover all these neat things. Okay, so curiosity pays off here. All right. So here's really the pièce de résistance, right? So so this was really a discovery by Nikos, and Nikos finally solved our problem of the additive business. So you don't need silver, you don't need to derivatize the compound, you don't need to change the chloride into anything else. All you need to do is use what is called HFIP, or hexafluoroisopropanol. It contains fluorine atoms, and it makes the OH bond very useful to bind with electron density of around other atoms. So it kind of has a pulling effect. Okay, so what you use is the neutral chloride, and you use a little bit of HFIP, and what the HFIP does is it slightly pulls the chlorine away. So slightly creating kind of like the magic tool around gold without having to completely remove the chlorine. Okay? And in fact, this transformation, so the formation of the cycle, is usually done gold chloride L plus silver, or gold OH NHC plus H plus to remove the water. Okay, here you don't need to do that anymore. So you save steps in derivatizing the gold, and all you need to do is just add a little bit of HFIP. And that's the magic ingredient. Okay, so Nikos was really a superb chemist, or is a superb chemist, and he actually got a picture of that. He got a molecular arrangement, he got an X-ray structure of how the interaction of HFIP is with gold and the chlorine. So it elongates that, so that bond is elongated versus the neutral. All right, so let me tell you a little bit about something that I've never really disclosed publicly, and that's our use of machine learning. Okay, so making it a first here is probably appropriate. And it's addressing a couple of problems, a couple of problems I have with my students, actually. So my students, they're very motivated, they're very gung-ho, they think they're very bright, and what I need to tell them in using machine learning and algorithms in trying to guide their chemistry is I need to tell them to leave their brains at home, to not think, because you need to let the magic or the algorithm work its magic. Okay, so here this is an algorithm guided optimization, and I think this will be, or is already, to a large degree, a major use of machine learning. Okay, so it's essentially an algorithm telling you what the best optimum combination of all possible variables is to get you to the end game. And our end game is the synthesis of that compound. Okay, a bunch of variables, a bunch of compounds surrounding our organic spinach around platinum. And what we do is we do 5 experiments. 5, that's it. And we do at random. So we're not trying to do the best, we're just trying to get 5. And then you feed that to the algorithm. So those are 5 entries. So this is called a training set. Okay, and the machine says, okay, do these 10 under those conditions. So we do the 10, and you get here 99 of the desired product. Okay, may not be the optimum, but 99 is pretty darn good. Okay, and the reaction conditions are kind of weird because we would never do a reaction at 34 Celsius. Who would do that? 37, yeah, okay, but 34, okay. Reaction time is 3 hours. Catalyst loading is fairly low. It's less than 1%. It's actually 10 times less than that. We figured it would have taken us between 30 and 40 reactions to do that, having at each time a bias, right, and learning and all that. It took us, well, it took the algorithm 11 reactions, but I don't remember which order that was. Okay, so it saved us an incredible amount of time. Okay, and that's through machine learning. So, and optimization. All right. All right, so let me tell you what I just told you. All right, that's usually something. So we started looking at this by curiosity, for sure. I mean, I was never at the offset interested that much in gold chemistry. In the lab, this is a Franco-French collaboration. So 2 of my students were French. One was interested in the organic, and the other one was interested in the inorganic part. So he was interested in making compounds, and the other one was interested in using the tool. And that's where that came about. We've been doing that chemistry since 2005. So yeah, it's been a while, and we're still developing stuff, right? We're really proud of the weak-based thing. And us scratching the mechanism has allowed us to use that approach with a variety of other metals. So we've made it much more general than just for gold. So mechanism is important. Always asking the question how and why are really important. As I say, I'm kind of mean. I ask those simple questions. And then I'll walk away. It's been exemplified with a variety of metals, I've told you. And we can do now catalysis at levels of parts per million. So I will remind you that in palladium chemistry used in medicine, the threshold of tolerated amount of metals is 10 parts per million in a drug. Right? So that's the allowed amount. We do catalysis with much less than that now. We do 1, 2. In the platinum chemistry I've shown you, we do with less than 1 part per million. So that means that for us, what's regulatorily acceptable is you can leave the catalyst in the soup. Okay? We try to recover stuff as much as possible all the time. But if we were just following rules, that would be allowed just to leave the metal in there. Okay? So that's actually allowed us to go towards sustainability for sure. But sustainability has led to innovation. I guess we've recognized some accidents that have occurred along the way, and those have actually been much more interesting. So serendipity, again, is a very important thing, and we need to recognize the importance of that. All right, so if you've never been to Ghent, so this is a classical Flemish architecture, right? So reminding you of the great masters, right? So this is the downtown with the, I guess, the basilica, so the cathedral in the back. This is the Lay River. So people I've mentioned along the way, people who flipped the bill, again, and some collaborators, some very important collaborators in Ghent and around the world, so in KAUST for Luigi and his computational help. Lastly, thank you again for hosting me here and allowing me to speak to you about this crazy thing about destroying gold bars and hopefully making tools that are useful to make drugs and anti-cancer things and things like that. And thanking you all for your attention. Thank you.